Now we'll introduce the t-factor. And before you watch this video, make sure that you have watched example of sampling distribution, because this video will build upon that. And also for this section, you might want to have a t-table available. So, just to repeat, in our previous example, we had a population with a known mean of 100 and a known variance. And we had a sample with a sample mean. And we used the standard deviation of the theoretical sampling distribution that is normally distributed to calculate an interval between which 95% of sample means from this population should be. And we concluded that it was not likely to get a sample mean of 81 from this population. Now we will redo this thought experiment with some other assumptions that might be more similar to what we have in real life. We still imagine a population with a mean of 100, but this time we don't know the population variance. And we still have a sample with a size of 16 and a mean of 81, but surely if we can calculate the sample mean, we can also calculate the sample variance. And just for convenience, we use the same numbers as in the last example. So the sample variance is 1296, the same as our population variance was in the last example. And we still have the same statistical question. We ask, is it likely to get a sample mean of 81 if we take a sample of 16 from a population with a mean of 100? And we still have a theoretical sampling distribution, but how can we calculate the variance of the sampling distribution if we don't have the variance of the population? Well, we can't. What we can do is to use what we've got. We have a sample variance, which is an estimate of the population variance. Therefore, we can estimate the variance of the sampling distribution by using the sample variance instead of the population variance. Our estimate of the variance of the sampling distribution is 1296 divided by 16, which is 81. So our estimate of the standard deviation of the sampling distribution is the square root of this, which is 9. And we have seen these numbers before. They are the same as in our last example. However, we have a problem here. In the last example, when we did a theoretical sampling distribution, we knew the population variance, and therefore we knew what the variance of the sampling distribution was. In this example, we did not know the population variance, but we had to estimate it with a sample variance. And this means that we introduce an uncertainty. Instead of using the theoretical standard deviation of the sampling distribution, we use an estimate that is based on our sample. This means that we can no longer use these numbers 1.96. Because of the uncertainty in our estimate, we have to make this interval a little bit wider. And how much wider, you might ask? Well, we find the answer to this by introducing the t-factor. And we will now take a look in the t-table. You should have received a t-table that looks something like this. In this table, you have a lot of t-values for different p-values or probabilities and different degrees of freedom. And to really understand the t-table, it can be valuable to look in the last row where the degrees of freedom equals infinity. Here, in the column for a p-value of 5%, you find the number 1.96 that you recognize from the normal distribution. The t-distribution for infinite degrees of freedom is exactly the same as a normal distribution. But a t-distribution compensates for small sample sizes, that is, when the degrees of freedom is less than infinity. Quickly, also note that this t-table is two-tailed, whereas the table of the normal distribution that we looked at earlier was one-tailed. You can easily figure out if a table is two-tailed or one-tailed by finding this number 1.96 and see what p-value it corresponds to. Here it is 5%, and that means that we get the probability for both the tails in the distribution. Now let's go back to our example. Here we had a sample size of 16. That means that our degrees of freedom is n minus 1, that is 16 minus 1, which is 15. Now look in the t-table at 15 degrees of freedom and for our critical p-value of 5%. Here you find the number 2.13. This is our critical t-value for a p-value of 5% and 15 degrees of freedom. Instead of using this number 1.96, we use our critical t-value of 2.13. And by putting this in our equation, we get new limits that are 80.83 and 119.17. And you see now that our sample mean of 81 lies within this interval. So our conclusion is that it's not unlikely to get a sample that deviates this much from a population mean of 100. So by not knowing the population variance, we had to estimate it with a sample variance. And this introduces an uncertainty which we take into consideration by using the t-factor. And in this case, the uncertainty was big enough that our conclusion changed from the situation when we knew the population variance.